Hello, my name is Brittany Nkounkou, and the work in this presentation is joint with Stephen Longfield, Rajit Manohar, and Tate. And I'm going to be talking to you about how we can prevent computer chips from catching on fire. So most computer chips in use today are clocked, in which a global clock signal is sent to all the processes on the chip telling them when to execute. Alternatively, chips can be self-timed, where on-chip processes tell each other when to execute via local message passing between one another. And one advantage of designing chips in this way is that self-timed circuits achieve average case timing behavior, whereas clock circuits exhibit worst case timing behavior because the clock is bottlenecked by the slowest process on the chip. Another advantage is that clocked processes often have to be made complex in order to adhere to the timing constraints placed on them, whereas those in self-timed circuits can remain simple and robust. And this simplicity, together with the fact that we don't have to put a clock on the chip, allows for much greater power and energy efficiency of self-timed chips. So those are just a few advantages of using self-timed circuits, and as you may have guessed, they come at a cost. And that cost includes the need for more complex reasoning about synchronization. So the mental model for reasoning about clock circuits is like that of sequential programming because the clock can give us some guarantee of the ordering on the chip processes, where on the other hand, that for self-timed circuits is like concurrent programming because processes are executing at arbitrary times with respect to one another. And we know that reasoning about concurrent programs is relatively difficult. And in this case, getting that reasoning wrong could potentially lead to a chip catching on fire. So the purpose of this work is to prevent these and other on-chip errors from happening. And we do so by analyzing the high-level specification of a self-timed circuit and determine whether or not it is erroneous. And currently, chip builders are performing this analysis by hand. So a main contribution of our work was to build a tool that does this automatically and accurately. So to get a sense of how this tool works, let's first take a look at how these specifications are created. So communicating hardware processes, or CHP, is the name of the language commonly used to build these specs. And in this language, we have channels, which are what processes use to communicate with one another. And in a typical system, data is going to be passed along these channels, but for now, we're just going to stick to dataless communication. So with this, programs then consist of a program that sends on channel A, a program that receives on channel A, the sequential composition of programs, parallel composition, the infinite repetition of a program, the program that does nothing, and there's more you can read about in the paper. And so the overarching idea of how these constructs work is that sends and receives are blocking processes used to enforce points of synchronization between two parallel programs. So for example, suppose we have this program, P followed by P prime, in parallel with Q followed by Q prime. And suppose we want to enforce synchronization between the two at these 2 points. Then we can do so by inserting a send on channel A in one program and a receive in the other. And so with this, we would then expect this program to proceed by having P and Q execute in parallel until the blocking synchronization points are reached. Then at this point, the send and receive on channel A will proceed together. And finally, P prime and Q prime execute in parallel. So that's generally how sends and receives work. And in building an operational semantics for CHP more formally, we'd ideally like the following rule to always be true. And this is actually the case for Hoare's language communicating sequential processes, or CSP, which is what CHP is a variation of. But the reality is, in CHP, there are certain contexts in which this rule does not hold. So for example, suppose we have 2 sends and 2 receives on the same channel all in parallel with one another. This program would proceed without error in CSP, but in CHP, it can lead to an error that could cause a chip to catch fire. And this is because of hardware limitations. More specifically, in CHP, channels are limited resources shared by all concurrent processes. And if those resources aren't used correctly, then certain on-chip errors can occur. So in making our CHP semantics more formal, let's dig a bit deeper and see how channels are implemented in hardware. So a dataless channel A is implemented by 2 wires, A bar and A hat. And communication across those wires follows a 4-phase handshake protocol that looks like this. So first, a sending process sets and holds a bar high, indicating that it has entered the synchronization point. Then a receiving process will acknowledge this and also enter by setting and holding a hat high. Next, the sending process will temporarily set a bar low and release it, indicating that it has exited the synchronization point. And finally, the receiving process will do the same with a hat, setting it low and releasing it as it exits. And upon observing that a hat is set to low, a sender can proceed to start another handshake on that channel if it wants to. So to distinguish between these 4 different phases of the protocol, we add active send and active receive constructs to our language. And so with this, we would ideally like the following rule to always hold, where when we have a send and receive in parallel, the send steps to an active send, then the receive steps to an active receive, followed by the active send completing and the active receive completing. But as was the case before, this rule does not hold in all contexts. So to see why, let's look at what each individual process is doing during the handshake. So again, the sender first drives a bar high, then the receiver drives a hat high, followed by the sender driving a bar low, and the receiver drives a hat low. Now, suppose we have a second receiver in parallel with these 2 processes. Then upon observing that a bar is set to high, the second receiver can join the first receiver in setting a hat high without error. But when a bar is set to low, one of the receivers can react to this sooner than the other, driving a hat low while it is still being driven high by the other receiver, causing a short circuit. And so similarly, you can see in the paper what a glitch is and how certain CHP constructs can cause a glitch to occur. So in precisely formalizing when a glitch or short circuit occurs, we have to incorporate into the semantics the fact that channels are limited resources. And one way of doing this is by including state in our operational semantics. So we define our state semantics as steps from a program in state to another program in state or an error. And here a state is a mapping from each a bar and a hat to a natural number indicating how many processes are actively driving that wire high. So for the rule that steps from a send on A, according to the protocol, it must be the case that a hat is low, or that it maps to 0, meaning any previous handshake on the channel has completed. In addition, we take into account the value of a bar, and when we step to an active send, we increment it, indicating that this process is now actively driving a bar high. Now for the active send to step, the protocol requires that a hat is set to high, or that it maps to a positive number, meaning the receiver has received the communication. Then the active send can proceed, and for a short circuit not to occur, it must be the case that a bar equals 1, indicating that this process is the only process currently driving a bar high. So when it proceeds to drive a bar low, it won't cause a short circuit. And so when we take this step, we map a bar back down to 0 because the active send releases its hold on a bar. So we also want to include in our semantics the rule where a short circuit does occur. And so we have this rule, where when a bar is greater than 1, this indicates that there are other active sends driving a bar high. So when this particular active send proceeds with its handshake by driving a bar low, a short circuit may occur. So those are the rules for sends, and we have similar rules for receives. And so these rules and a few others constitute the Chp State Semantics, and these semantics are commonly used and accepted by the asynchronous circuit community. And further, they have been formally proven to accurately reflect the hardware. And so with these semantics, we can determine whether or not a CHP program can lead to an error. But in building this tool, consider the case of parallel programs. A naive analysis would consider all possible interactions between the different parts and blow up exponentially in time and space. So instead, we'd like to do something smarter. We'd like to reason about these programs compositionally. So we want to look at the different parts individually and then use some local information there to infer the behavior of the program as a whole. But remember that Chp State Semantics associates each transition in the system with a global state. And so reasoning about these parts locally is difficult. And another shortcoming of the state semantics is that they can't express simultaneous actions, which are inherent in the cause of errors. So because of these issues, we developed a new Chp semantics that is more suitable for global reasoning, and this is another contribution of our work. So the Chp trace semantics, as opposed to the state ones, don't have a global state, and instead we encode information onto the transitions between programs with the label L. And that label L can be idle, which means no communication is taking place, a step S indicating that a communication action step is taken, we can have two or more actions happening simultaneously, and more. And a step is defined as a move made by either a sender or a receiver, and a move is either to start using, to actively use, or to finish using a channel. So with this, we include rules for a sending process to start and finish using a channel, and note that in addition to these rules not having any global state, they also don't have any required conditions, which allows us to reason about them locally even easier. So in addition to these, we also have the rule for a sending process that is ready to use a channel to idly wait. We also have the rule for an active send to actively use a channel. And of course, we have similar rules for receiving processes. We also have the rule that takes two parallel processes transitioning together and just composes their individual labels together, which captures simultaneous actions. And so given these rules and a few others, we reason about them locally. Then at the global context, we apply filters to these transitions. So a label is said to be compliant if its transition is traversable in the hardware. And an interferent label indicates that if the transition is taken, it can cause a short circuit to occur. So using these filters, given a transition with label L, if the label is compliant and not interferent, then the global program can make that transition. On the other hand, if the label is compliant and it is interferent or erroneous in some other way, then the global program will error. So let's take a look at some examples. Consider a sender actively using a channel while a receiver is finishing its use. This label is not compliant because the protocol says that the sender has to finish before the receiver. So if we make that the case, where the sender is finishing its use while the receiver is actively using the channel, then this transition is compliant as it respects the protocol, and it's also not interferent because no short circuit occurs. Now, suppose instead of a sender and a receiver, we had two receivers, where one receiver is finishing its use while the other is still using the channel. Then this label is still compliant because the protocol is respected since no sender is still using the channel, but it's interferent because a short circuit occurs between the two receivers. So that is generally how the trace semantics work, and given the fact that they're so drastically different from the commonly accepted state semantics, we prove the two to be equivalent. More precisely, we prove that a program errors in one semantics if and only if it errors in the other. And this has been mechanically proven in Nkounkou for all CHP programs utilizing dataless communication. And so since the state semantics have been proven to accurately reflect the hardware, our trace semantics do as well. So using these semantics, we built an inferable effect system that is sound and complete in identifying glitches and short circuits. And so let's take a look at how the system works. So the effect of a program P is represented by a non-deterministic finite automata describing all possible traces of the program generated by the trace semantics we just saw. And we can infer this effect compositionally. So the NFA for a send on channel A consists of the following three states and the edges between them. And in addition, we also have the following self loops on each state, but we hide them for brevity here. And similarly, we have the following NFA for a receive on channel A, and we apply standard automata operations for the other CHP constructs. And so in the case of parallel programs, we want to avoid that cross-product operation as much as possible. And we're able to do so because of the effective local reasoning that the trace semantics gives us. So for example, consider the following program. This is a 3-stage first in, first out FIFO buffer that takes in data on channel I, pipelines it through channels A and B, then outputs it on channel O. And so we can take the cross product of the first and second parallel programs as follows. And now at this point, instead of composing this with a third program, we recognize that channel A is used exclusively in this context. And further, this is the only compliant edge that mentions A. And since A is not used in any other parts of the program, we know that any other edges mentioning A will not become compliant in any other context of this program as a whole. So we can remove them. And another optimization is that this NFA is built lazily. So in this particular example, the unreachable edges you see here are actually never even explored. And moving forward, the next step is to collapse nodes and edges containing A because we know that no other parts of the program are going to interact with them. So we're left with this simple NFA. And the optimizations I just performed here turn out to be very effective for CHP due to the fact that channels are very rarely used across many different concurrent programs. And so finally, we compose this with a third part of the program and perform this same reasoning until we are left with this simple 3-state automata describing the synchronization effect of the program above. And note that without the optimizations, we would have expanded the NFA to a full 27 states. But by building this NFA compositionally and lazily, we never exceeded 4 states at any point in time. And so this is a prime example of the efficiency of our analysis. So using optimizations such as these, we built our tool and ran it alongside Spin, which is a pre-existing model checker that is particularly well suited for the CHP domain. And the results of this comparison are as follows. Our tool is shown in blue and Spin is in orange and red, where red indicates that the Spin analysis did not complete because it exceeded an entire half a terabyte of memory. And note that these memory and time graphs are on a logarithmic scale. So in most cases, our tool used less time and less memory to perform the analysis. And this is particularly true of the FIFO instances, which are very well suited for local reasoning, as we saw earlier. On the other hand, the token ring examples are adversarial to local reasoning because erroneous behavior can only be ruled out in the global context. And so Spin outperformed us on the larger of those instances. But one of the most notable results is that our tool shows that it is scalable and practical by being able to analyze the specification of a real self-time microprocessor. And it did this using less than 50 megabytes of memory, and it completed in about a second, whereas Spin read out of half a terabyte of memory after several hours. So these are our performance results. And at this point, it should also be mentioned that when we do consider data being passed along channels in CHP, which is typical of a practical specification, including the microprocessor analyzed here, then with some other CHP constructs that weren't presented here, we can enable data-dependent synchronization, which then causes our analysis to no longer be complete. However, using data for synchronization is not very common in CHP, so we still believe our tool to be practical. In conclusion, we have developed a new CHP trace semantics that is equivalent to the commonly accepted state ones, and we've used this new semantics to build an inferable effects system that determines whether or not a CHP spec can cause a chip to catch fire, and it does so scalably. And so in continuing with this work, we plan to extend our semantics proof of equivalence to include data, and we also plan to build a verified version of the analysis itself based on the formally verified semantics. And finally, there are a number of other aspects of the overall CHP development process that have yet to be automated. And as this language and self-time circuits in general are a relatively unexplored area of study, there's a lot of potential for some domain-specific techniques to be applied to the area, as we have done in this work. So that is it. Thank you, and feel free to contact us with any questions.